Bessel's differential equation of order nu is x squared y double prime plus xy prime plus x squared minus nu squared times y equals to 0 for some constant nu. This differential equation appears when you try to solve a Laplace equation on a cylindrical domain, and it also appears in many different contexts. Now, if you solve this using Frobenius method, you'll have to solve the initial equation, and the solutions will be nu and negative nu for the initial equation. And applying the Frobenius method, you're going to find that the solutions look like this, with positive nu and also for negative nu. However, if nu is an integer, then this becomes complicated because one solution looks like this, the other solution will have some logarithmic singularities. Now for this video, this will be part 1, where we're only going to try to solve this equation using Frobenius method for finding the one without the logarithmic singularity, and the next video I have planned will show you the other solution using the Frobenius method. Okay, so let me show you how you can get the initial equation and solve. The formula for the initial equation is this, and P0 and Q0, I'm going to show you the definitions. So first what you do is you divide both sides by x squared so that it looks like a standard form. Standard form means that y double prime has only 1 as its coefficient. And once you have the standard form, the coefficient of y prime is what we call px, coefficient of y is what you call qx. So we have these two functions, and lowercase p is x times capital P, whereas lowercase q is x squared times capital Q, and P0 and Q0 are defined as the evaluation of these functions at 0. In our case, we see that lowercase px is a constant function 1, so regardless of what value you plug in, you're going to just get 1. And for the qx, you get x squared minus 1, so if you plug in 0, you get negative 1. And plugging those into our initial equation gives you the following equation, which if you simplify, you get r squared minus 1, and its solution is r equals to negative 1 and 1. Which means that we will have a Frobenius solution of this type for r equals to 1. See, if the difference of these two numbers is an integer, then Frobenius theory says that the higher one will always have a solution, whereas the lower one, you may or may not have this Frobenius type solution. If it doesn't give you a solution, in that case the other solution will be this time some logarithmic singularity plus another series, and that's the one that I will be showing you in the next video. For now, we will just try to plug this into our equation, and we will try to find the values, the coefficients an. Okay, so let's do it. So we plug everything in here. We take y of x first. To plug in, we have to find y of x. We simplify it like that, and then we have to differentiate and also find the second derivative. Every time you differentiate using the power rule, x plus 1 comes down, and you get this as the derivative, and you differentiate again, n comes down, so this is the derivative, and you plug in these three functions into this equation. Oh, but before that, you want to split this x squared minus 1 times y as x squared y minus y. So after that, once you plug in all these series, this is what you get. And then we can move these x squareds and x inside, and if you do that, you see that all of these have n plus 1 as the coefficient of x, the power of exponents of the x, except for this third term. This one has x to the n plus 3, which doesn't match with the others. So what that means is I need to shift this. So what is shifting? Well, shifting is the following. We replace n by n minus 2, and if you do that, then n minus 2 plus 3 will become n plus 1. N will become n minus 2, and even this one will become n minus 2 equals to 0, and that gives you n equals to 2, and you get this new expression for the same series. So if you expand this series, after all, what is sigma? Sigma means you add this for n equals to 0, n equals to 1, and so on and so on. So if you actually wrote this out, it would be a0 x to the third plus a1 x to the fourth, and so on and so on. And this indeed is exactly the same. When you plug in 2, you get a0 x to the third. When you plug in 3, you get a1 x to the fourth, and so on and so on. So they're indeed the same exact series, and therefore I haven't done anything to it. Okay. However, now that we have this, and they are working with the same clock, I tend to think of these indexes as like clocks with you have 4 factories like producing these terms, and the first, second, and the fourth factories, they start at time 0, say that's like midnight, but this third factory, they start at 2 a.m. Okay, just keep that in mind, and let's see what that means. So we have this equation, and when n is 0, you get all these factories producing x to the first power term, right? So you get the x to the first power term. If you read what it does, is when n is 0, it's 0 plus 1, which is 1, and 0, which is 0, a0 x to the first power. And the second one has 0 plus 1, which is 1, a0, which is a0, x to the 0 plus 1, which is x to the first power. This one will start the workers here will start working at 2 a.m. So at 0, the midnight, they're not doing anything, so there's nothing here. And then when n is 0, you get a minus a0 x to the first power equals to 0. Now if you simplify this, you'll see that this indeed says this is 0, this is a1 x to the first power, there's nothing, that's 0, and minus a0 x to the first power, so this should be a0. And these two just cancel out, so this is 0, so this is already satisfied. Okay. However, the next one here says it should be 2a1x squared plus 2a1x squared plus nothing minus a1x squared equals to 0. And if you put them together, you get 3a1x squared equals to 0. And this should actually hold for some interval value of x. So for this to be true, you actually need a1 to be equal to 0. And so we get this conclusion. So what does that mean? Well, think of it like this. If a1 is indeed 0, if you set a1 as 0, that was our conclusion, it has to be that way, then the terms that are produced at n equals to 0, or the 12 midnight, are going to cancel anyways. So there's nothing that's going to be produced if you combine them. And also at 1 a.m., when n is 1, all of them will just add up to, again, 0, assuming that a1 is 0. And therefore what that means is only starting at n equals to 2, which corresponds to x to the third power, these things produce something that's non-zero. Okay? So you have this, you start rewriting this for n equals to 2. Okay? So it's the exact same thing, and we just ignore n equals to 0 and n equals to 1. We just think about what happens after n equals to 2. Starting from n equals to 2, now that they all start at the same time, I can just use the single clock for all these workers to work together. So I put them together and I factor the x to the n plus 1 out, and that leaves you with this, which is which means, if I further simplify, it means that n squared plus 2n an plus an minus 2 will be the coefficient of some x power, and the theorem for power series says if this is true for all some value of x in an interval, then the coefficients have to be 0, and therefore you set the coefficient equal to 0, and the result is you get this recurrence relation. Solving this for the higher index, you get this recurrence relation, and this is called a recurrence relation because you can keep plugging in values to get the next one. So let me show you how this thing works. So let's say we have this. We can plug in n equals to 2. That immediately gives you that a2 is negative 1 over 8 times a0, where a0 is some unknown number. So that's arbitrary. So we have a result. We can now replace a2 by something times a0. And also you can plug in 3 into this recurrence relation and find that a3 is something times a1. But what is a1? We deduced that a1 is equal to 0 already, right? So a3 would be 0. a4, you can do the same thing. a4 is negative 1, 4 times 4 plus 2, which is 4 times 6, a2. And then because a2 is negative 1/8 here, I can replace, and that gives me this relation. And you can go further and find out that a5 is 0, and then if a5 is 0, a7 will be 0. So we see that all the odd terms will be 0, a1, a3, a5, a7, they're all 0. Whereas a6, if you write them out, you start seeing some pattern. Okay, so we conclude that the odd terms vanish, but the even ones, if you rewrite them carefully, you end up with this term. And this is obtained by first looking at 642. All of these are even, so I can factor a 2 to the third power out. Again, these are all even, so I can factor 2 to the third power. So you end up with 2 to the sixth power. And what's left is 3, 2, 1, and 4, 3, 2. These are 3 factorial and 4 factorials, right? So you can rewrite it in this form. And if you look at the relationship between this value 6 and this value 6, they're the same, right? So if I say you have some even number 2k, that same 2k will be here. And 3 is exactly half of 6, so it will be a half of 2k, which is k. And 4 is 1 more than 3, so it's k plus 1. And then this 3 again is half of 2k, so you get this as your solution for all the an's. Therefore, now I can replace this into our original starting point. We started out by saying that the solution should be a Frobenius type, which is they should look like this, right? So I can replace an by what we just found out, and if I replace this an by what we just found out, we can get the following thing as a solution, and we can also multiply 2 top and bottom to make this as x over 2 to the 2k plus 1. Yeah. So if I, or since this is going to be a solution of this differential equation for any a0, we just choose this to be 1/2 so that you can simplify it in this way. And this is what we call the Bessel function of the first kind with index 1. And we just solved this differential equation. We didn't fully solve it. We only got half the solution. We need to find 2 solutions for second order differential equations and 2 linearly independent solutions. So we only found 1 solution, but that's a start. Okay, so I want to conclude by saying that this function, usually written in this form, this should be n. It's written in this form, and that is called the Bessel function of the first kind with index 1.